Cryptography. That's a nice topic after lunch, right? Who feels comfortable with cryptography and everything around that? 2 people, 3 people. You can just go for a surf, and I'll try to explain the basics of cryptography in this talk. I will not go into detail, and I might simplify certain things, so don't expect to be an expert after this. But it's good to know the basics of certain cryptography thingies. It's very difficult to say cryptography for me. So let's get started. My name is Bellen. I'm a developer advocate engineer at Auth0, and if you've never heard of Auth0 before, shame on you. No, we're an identity as a service provider, which basically means that we try to make it as easy as possible for everybody to implement a secure authentication so you can focus on building your apps. I'm a Google developer expert, and I organize a few events, Frontiers in Belgium, which are meetups, and the identity and security meetups in London. If you're ever in Belgium, if you're ever in London, join us, we're fun. And you can find me on the internet as Sambego. This is a JavaScript conference, so if you want, you can npm install me. So at sambego/about-me, you'll download half of the internet, and when that's done, you can see a bit more about myself, and find the link to these slides as well if you want to. I have some cat stickers, so if you want to have cat stickers, just send me a picture of your cat, your dog, your sea turtle, whatever, an animal, and I'll give you some stickers after this talk. Okay. So, disclaimer, I already said this, I might simplify certain things because cryptography is very difficult, it gets very complicated real fast, and I just want to stay on the surface of this. So what we're going to be seeing today, hashing, signing, encryption, and Jose. If you've never heard of these things, perfect. If you have, also perfect. So, hashing. Hashing, an hashing algorithm is a mathematical algorithm that maps data of an arbitrary size to a bit string of a fixed size. Doesn't matter how big your string is or your content is, the end result will always be the same size that comes out of this algorithm. The initial data is often called the message, and the outcome of the hashing function is called the hash or the message digest. And a hashing is a one-way function, which means you can put in something in a hashing function, you get out something, but you cannot reverse the thing you just did. Your hash cannot be reversed to get the original content you put in that function. So if you input dog, you get a certain string. If you put doggo, or if you put in the quick brown fox jumps over the lazy dog, you all get some output, and they're all of the same size. Doesn't matter if it's a 3-letter word, or a whole sentence, or a whole book. I'm not sure about the whole book, but it should all be the same size. And you cannot reverse it. It's a one-way directional algorithm. A bunch of them are these ones. There's a bunch more. You might have come across them. Yeah. So there's another type of hashing. It's called keyed hashing. And it's a little bit different, but it's also the same. It's an algorithm. It's one-directional. You get a fixed thingy out in the back of the function. But keyed hashes lets you validate the integrity and authenticity of the content of the hash, which means that you can validate that the content of that you're trying to validate is not been tampered with. In order to compute a keyed hash, you need a secret key, something that is secret, which you don't pass on to other people, and you save it somewhere securely for yourself. So if you take the same thing as we saw before, we basically have the same, or we have an algorithm that outputs a hash, but it also wants that secret. And based on that secret, the output, the hashes, is going to change. So if I change my super secret to some other secret, the hash will not be the same, even though the input was still the same. For example, we have the quick brown fox, etc., as an input, and we use super secret as a secret. The algorithm will output a certain hash. If you use another secret, it will output another hash, which means that you can validate that somebody has or has not changed something in the original input. Okay, the inside of this algorithm looks a bit like this. Your secret key gets split into two different keys, an inner key and an outer key, and then you just make a first hash, use that first hash to create the second hash, and that second hash is an output. This is specific to HMAC, but you don't really need to know this. The thing you need to know is that you get a fixed hash outside at the end of the function. So some key hashing algorithms are these. You might come across some others. There are way too many algorithms to sum up in this talk in 25 minutes. So let's move on. So all these algorithms have very difficult names with a lot of letters and a lot of numbers. And sometimes it's confusing to know what they mean. So if you break down this algorithm, HMAX SHA-265, which should be 256, it's keyed hash message authentication code. So we're going to create a keyed hash message. And it's using the secure hash algorithm to do this. And we're getting a 256-bit output, basically. So all these algorithms are basically, you can break them down into certain parts, and they all tell you a certain thing about the algorithm, what it's doing, which algorithm it's using, bit size, and stuff like this. Hashes are often used to store passwords. For example, if you want to store passwords in a database, by now we should all know to not do this in plain text. Who does that in plain text? Nobody. Hashes are often used for this because it's a one-way algorithm, so you can store it in there. And even though if your data gets stolen, which I hope it doesn't, people can still not know the password because you cannot reverse it. OK, on to the next topic, signing. Digital signatures offer all properties of keyed hashes plus cryptographic non-repudiation, which means that you can also check the integrity and authenticity of the output, but it's also cryptographic non-repudiational, whatever it is. Which means cryptographic non-repudiation enables the other parties than the signer to check the signature's validity. HMACs use the secret to create those hashes, but if you want somebody to enable to check the output of that hash, you also need to share that secret. And we all know the more you share a secret, the less secure your secret gets. So it would be nice if we could do the same thing without sharing our secret with other people, with third parties. Signatures of digital signatures allow you to do this. They use a public key and a private key to do this. They're asymmetric cryptography, which is basically the same as saying I use a public key and a private key to do stuff. The signer creates a signature using the private key. So you, the person who's going to create the signature, you're going to use your private key to create that signature. And then you're going to just send your signature to whoever needs to use that one. And that person or that party can use your public key, which is something that can be publicly available, to check the validity of your signature. That way, you don't have to share your secret. You don't have to share your private key. You only have to share your public key, which can only be used to validate the output, but you cannot create a new signature with that public key. For that, you need a private key. And a signing algorithm is usually a collection of 3 algorithms, or maybe more. A key generation, something that generates the public key and the private key. A signing algorithm, something that makes a signature. And a verifying algorithm, something that knows how to verify those signatures created by that algorithm. So it might look something like this. You have your input, a hashing algorithm. You sign that with a private key, and you send that output to whoever needs to receive this to verify the input. And then the person who wants to validate is going to basically use a verifying algorithm to get a hash. It's going to hash the original input, and if those hashes match, they know that the content has not been tampered with. And it's going to use a public key to verify the signature, not the private key. Signing algorithms. So the most commonly used public key cryptography approaches when signing are RSA, elliptic curve, and Edwards curve. There's a few others, but these 3 are more common. RSA could be a few of these. And the good thing about them is they're fast. They're CPU friendly. They have a good support. RSA has been around for a while. The bad thing is they require longer keys because you need a minimum of 2056 bits to have them a bit more secure. So your output will be longer, your process will be longer, your computations will be a bit more intense. And as I said, these signatures are a bit longer because we need these 2056-bit algorithms. Elliptic curve, they're shorter for the same equivalent of security as RSA. They have shorter keys, shorter signatures, but they're also a bit more complicated, so they take a bit longer to compute. And then Edwards curve, they're the best for signing performance, but they're relatively new, so not all libraries that you might want to use in your project might support them. It's new, so it's coming to most libraries, but it might not be there yet. That's a downside, but not forever. All right, we've seen hashing, we've seen encryption. Let's go on to encryption. We've seen hashing, we've seen signing, let's go on to encryption. When encrypting data, we can not only ensure the integrity and authenticity, like keyed hashes, but we can also be sure that the data will stay secret for outsiders. So people who should not know the contents of the data cannot know when it's encrypted, or should not know. So you need either a private key, a secret key, or a password to read the data to decrypt the encrypted data. The encrypted message is often called a cipher. So if we refer to a cipher, it's basically the end result of an encryption algorithm. It's the output of that algorithm. It's the encrypted message. And there's symmetric and asymmetric encryption. Symmetric encryption, some examples of those are when you want to encrypt your file system, your hard drive, or Wi-Fi protected access, WPA, database encryption. Anything that has a lot of content is usually encrypted with a symmetric algorithm, which uses a secret key or a password instead of a public and private key. These are a few of the algorithms. And it works a bit like this. Your input gets encrypted with a certain algorithm. You get the output, and then if you want to decrypt it, you use a decryption algorithm. But they both use the same secret key or password. You don't have a separate key for encrypting. You don't have a separate key for decrypting. They use the same secret. That's why it's symmetrical. Asymmetric encryption, on the other hand, the sender asks for the receiver's public key first and uses that public key to encrypt the message so that the receiver can use his private key to decrypt the message. So you have two different keys that work with these kind of algorithms. So when the receiver receives a cipher, they use their matching private key to decrypt the message. Encryption with the public key, decryption with the private key you own, and you will keep on owning. The public key is public domain, or could be public domain. So anybody can use your public key to create an encrypted message, send it to you, and you'll be able to decrypt it with your private key. And this means you will be the only one to be able to decrypt that with your private key. So if you take the example of we had before, instead of using one shared secret, we now use a public key and a private key, public for encryption, private for decryption. So a little bit detailed example of RSA, because it all sounds fancy, but how does this actually work? How can we use a public key or a private key, and how does the magic behind that work? It's quite complicated, so I'm going to try to explain it a bit more simplified. So the first thing you do when you work with asynchronous algorithms is generating keys, your public key and your private key, so you can do stuff with them. So cryptography is usually based on large prime numbers. In this example, I'm going to use small prime numbers, just so it's a bit more readable. But in practice, you're going to use very, very large numbers. So the first thing we do, we want to create a set of keys, a public key and a private key. So we create two prime numbers, and these are going to be huge. In this instance, 61 or 53. And we're going to calculate a lambda, which is the least common something, I forgot the name. But it's basically a mathematical function you run with those prime numbers. You get the result 780. You keep those numbers. You don't give them to anybody, but you use those to generate the public key and the private key. Then the public key basically contains the modulus and the public exponent, and the private key contains the modulus and the private exponent. And by just saving these pieces of data, which we created from the top part, the secrets, we can later on use them to encrypt or decrypt certain messages. Remember that there's the public exponent E and the private exponent D in the public and private key. So if you want to use a public key to encrypt a certain message, we're going to take those numbers, that data in the public key, and we're going to do a mathematical computation. In this case, it's M E mod N, where M is the message, E we find, E and N we find in the public key. These are the things we just put in the public key right here. And if you do this computation, you end up with a result, which is the message digest. It's the cipher of the encryption algorithm. And if you want to do it a bit more complicated, you're probably going to take your input and then convert that to a string or binary and then to a big integer and do the whole thing again. But the basics stay the same. You have your big number and you use that certain function to create an output, which is 2183 in this case. Then if you want to use your private key to decrypt it, we know that the private key has two things in it, the modulus and it has D in it. So we can use a mathematical function to run on the input. And if we do this, we should be able to get the original value back. This is because the N value, the D value, the E value in your public key, they're all derived from those secrets we created in the beginning when we were creating our keys, the two prime numbers and the lambda. So we input the cipher we got back in the previous example, and we should be able to get back 1, 2, 3, 4. If you're very good in math in your head, you can try to do this. Otherwise, just believe me that it's true. Again, usually you're not working with numbers, so you might want to get some text or something else out of it, so you have to do some conversion between certain types. But the essence is still big number, do some mathematical operations, get another number, and use those thingies. So if we would look at an example, this is the same numbers that we saw earlier, and then the encryption is just 1616 to the 17th, and then modulus 3233, I think. And the decryption is the same function we saw earlier, and we can see that this works. But in reality, we're working with very big numbers, so the numbers might be something like this. Notice that these are numbers with more than 150 digits in them, so they're quite large. They're all quite large prime numbers. Okay, asymmetric encryption. Use cases are TLS, VPN, SSH. You might be familiar with those. Those use public keys and private keys, as you might know or might not know. Some algorithms. And it's worth to say that symmetrical algorithms are faster than asymmetrical ones, just because of the amount of math that's included in doing something asymmetrical. And like I said before, when you want to encrypt a big piece of data, you're going to use something symmetrical, because it would be not possible to do that with asymmetric algorithms. So, Jose, the name of the talk. What is Jose? It's JSON object signing and encryption. So basically, it's just a group of standards created by some governing body of the internet, which combines a few standards based on JSON. Why JSON? The JSON format is often used for serializing and transmitting structured data over a network connection, which basically means we all know how JSON works. We all have worked with JSON in the past. We all know how to do that thing. And it has excellent support in most programming languages. Even though it was born out of JavaScript, most programming languages now support JSON in one way or the other. So, like I said, it's a collection of standards, JSON Web something. You might have heard of a few before, JSON Web Token being the most common one, but there's more than just tokens. There's JSON Web Keys. And what this basically means is a way of sharing public keys over the internet in the form of JSON. And this might look something like this. This is a public key serialized to a JSON structure. And if you paid attention, you might see that there's the N and the E value, which we talked about earlier, which is the public exponent and the modulus also in this. So this is a public key. It has some more information like a key ID and certain other things like which algorithm can use this and the usage for signing in this case. But it's a JSON structure which contains all the information of a public key. The next one is JSON Web Signature. And you might have seen this with JSON Web Tokens. It's usually base64.base64. Some random stuff, which is also base64. So if you look at a JSON Web Signature, it's 3 parts. The first one, the header, the payload, and the last part, the signature. And this could be a JSON Web Signature, base64.base64.base64. Looks all random data. It is not. If you would try to decode those base64 thingies, the first one, the header would be a Jose header. And you would get something like this, the algorithm that's being used in this signature. If you would do the same with the second part, you would get something like this, some JSON content, foobar, anything that's valid JSON could be the payload of a JSON Web Signature. And then the third part is the last part in the string as well, is basically just the actual signature. So you take your header, you take your payload, run it through a certain algorithm that's going to create a signature, and you're going to use a secret or a public and private key, depending on the algorithm. And you're going to paste this in the end, so you can verify that the content of your payload and your header has not been tampered with using that signature. The next one, JSON Web Encryption. We've seen signatures, we've seen keys. There's also something called JSON Web Encryption. And instead of 3 parts, it has 5. The header, the encrypted key, the initialization vector, ciphertext, and authentication tag. And it's good to know that JWEs, JSON Web Encryption thingies, use 2 kinds of encryption. They use the content encryption key, which is the second part we saw earlier, is usually encrypted with an asymmetrical algorithm because it's usually a short piece. It's just a key, a content encryption key. The second, which is the second part, and the cipher, the actual message which we encrypted with this JWE, is encrypted using a symmetrical content encryption key, the SEC, so it's CK, SEC, I don't know how to pronounce it, but that's something symmetrical because you sometimes want to encrypt a large piece of text or content in a JWE, so you need to do this symmetrically. And that's the fourth part of your JWE. So how does this work? The first part, JSON header, the same thing, you have an algorithm, an encoding, and maybe a key ID. The algorithm you use to decrypt the content encryption key, which is in the JWE. The encoding tells you which encoding can use that content encryption key, and the key ID is often a reference to a public key available somewhere, which you can use with the first algorithm. So to decrypt the content encryption key, the second part, you're going to check in your header which algorithm do I need to use to decrypt this. You're going to pass along your content encryption key, which is the whole second part of that string, and you're going to use the private key that you have available somewhere, which is referenced as a key ID in your header. And to decrypt the cipher, you're going to check again in the header which algorithm do you need to use, pass along the cipher, the actual encrypted text in this JSON Web Encryption thingy, pass along the content encryption key, which is a thing we just decoded in the previous step. And then some algorithms require a initialization vector, some don't. So if you don't have one, this will just be empty, an empty string. And lastly, the authentication tag. That's very basic what's happening. You first decrypt the content encryption key, which is inside the JWE, and then you use that key to decrypt the actual cipher, the actual content of your JWE. Both JSON Web Signatures and JSON Web Encryptions can be serialized as compact, the ones we saw earlier, the string with the dots in the middle, or as JSON. This would be a JWS serialized as JSON, and this would be a JWE serialized as JSON, and you might see that they have the same info, the IV, the ciphertext, the tag, the encryption key, it's all in there, but it's just a bit more readable, even though the compact serialization is used more because you can just send it with requests, it's smaller. Lastly, JSON Web Token. If you work with APIs, authentication, you might use this, you might have heard of this. And a JSON Web Token is basically a JWS or a JWE. JWS is the more commonly used version of a JSON Web Token, which if we would decode the header, we would see something like the algorithm, and now we just say that the type is JWT. It's a token. We're going to use this as an access token, as an ID token, as some kind of token with our API or whatever use case you have for those tokens. So if you would decrypt the payload of this JWS, and it would be an access token, you might see something like this. All data that's related to using it with an API, audience, scope, the issuer, stuff like that. If you would use it as an ID token, it would contain a bit more information about the identity of a user that has been authenticated. So you would see more data in the payload, which is related to a user, like a nickname or name or a picture, stuff like this. But it's all valid JSON, can all be put in the payload, and by using the signature, we can still validate that nothing has been changed in the middle of whatever network process you had going on, so that it's still a valid token. Nobody tried to tamper with it. So to summarize, hashing compresses and makes it virtually impossible to get to the real data. So, for example, if you want to store data securely, like passwords, you're going to use hashing for that. Keyed hashes protect the integrity of the data because you need to know the secret, you need to know the key to get the same result over and over again. Digital signatures allow third parties to verify the validity and the origin of the data. Just because we're working with two keys, a public key, which we can share with everybody, and a private key, which we keep to ourselves, we can share these signatures, and people who have access to your public key can validate those signatures. Encryption allows only authorized people to read the data because you need, the message gets encrypted with your public key and need your own private key to decrypt the message, so only you can read the message. And JSON is a set of standards based on JSON that help us with signatures and encryption on the web, because JSON and the web, it's almost synonymous these days. If you want to see these slides again, jose.samvega.tech, they will be there for basically forever. If you want to learn more about JSON Web Tokens, we have this little website called jwt.io, which contains a bunch of information, a debugger, some libraries, stuff like this. We have a bunch of blog posts on our blog as well about anything authentication or encryption and a lot of different topics as well. That being said, thank you.